All right, Jim, let's get started. So we still have a few people joining here in the background. I will let them in for you over the next few minutes. Again, everybody, welcome to our next edition of Ambient Academy. This is Designing One Pipe Hydronic Systems, and it's going to be with Jim O'Donnell from HC9. This is going to be for one personal development credit, and we're happy to say that this has already been approved for Pi credit, so we're ready to issue certificates as soon as we get done with this. So if you do need a certificate, please reach out to either me or Jim, and we can get that issued for you. A couple things before we get started. Just a little spiel on Ambient. If you've not been involved in one of these classes before, Ambient is a collective, essentially, of HVAC design and implementation companies. And we are a national company at this point, from California all the way to the East Coast. Couple things about the call. If you would prefer to enable your camera, you can, although it's not required. We've changed things up a little bit where we have everybody muted. So if you'd like to ask a question, just make sure you put it in the meeting chat. And then towards the end or throughout, Jim will either periodically check it or he'll check it towards the end there and answer any questions you have. So again, make sure that you've joined this call with the same name that you've registered your Ambient Academy account with, just to make sure that when we're sending certificates back, or if we get an email from you about their certificate, that we have the right person and it's issued to the correct name. So without further ado, Jim, I will let people in as they come, but you are more than welcome to take it over.
Okay, thank you, David. All righty. Okay, gotcha. All right, that's always my nervousness. I know the presentation, I know the topic, I know the content very well, but it's like just always terrified my computer's going to freeze or whatever. So anyway, there's my contact information. My name is Jim O'Donnell. I'm a equipment salesperson. I work for HC9. I work in the Philadelphia market. Philadelphia, Pennsylvania, also cover Delaware and some other accounts down here. Previous lives, worked as a contractor, worked as a consultant engineer originally from the New York City area, also up in Buffalo. So anyway, been down here about 20 years now. So as David said, what I'm going to talk about, the world according to Jim, in 1 hour today is designing one or single pipe systems. As David mentioned, this has been approved in New York State for the Practicing Institute of Engineering for 1.0 professional development hours. With that information, you can determine if it's passable or eligible for the state that you would have your professional engineer's license in. So anyway, let's get started. So today the objective is just to go over single pipe hydronic systems and explain how they reduce first cost, how they save energy, and while doing that, they still will satisfy your space comfort conditions, your space comfort requirements. So just three broad strokes of the agenda of what I'll cover today. First, I'll go over single pipe systems and the three main hydronic systems, which are chilled water, hot water, and then with water source heat pumps. I put just the word condenser water because there's cooling tower water, and there is, water for, ground source systems, et cetera, like that. But it is condenser water with the heat exchanger. I'll talk about some design considerations for single pipe systems. And then lastly, kind of not for filler, but just some generic hydronic system considerations that, in my experience, they seem to come up over and over again. Just a few couple of reminders and tidbits. So quickly, just to explain the different hydronic systems, this schematic here shows a traditional two-pipe system. Just going through the components of it, you have a central boiler for heating, a central chiller for cooling. You have distribution piping, where you have two piping systems, there's supply and return. And then what I'm calling as terminal units, with one coil, these are providing the heating and cooling to your spaces. They can be fan coils, they could even be air handlers, et cetera, like that. So that's a two-pipe system. Just realize also too that you could have a changeover system. This could be just cooling only. This one here is a changeover with heating and cooling. Quickly going through a four-pipe system, what you've done now is just made two supply and return systems. One would be considered for cooling as chilled water. The other would be considered as hot water. And just want to point out that inside the terminal units, you now have two coils. They're two separate coils. They don't cross over like they do in a one-pipe system. And then also now you have two independent system pumps. Just to go through some more basic information about piping systems. For distribution piping, there's two types. There's a direct and reverse return. They can be either in one, two, or four pipe systems. What's depicted on the screen here is the direct system. So if you start on the left with your supply, your supply water travels to the first unit, comes out of the balancing valve, and then returns to the return piping system, and then travels to the left. As you can see, the piping that goes, the water that travels from route 1 has a much shorter route than route number 5. So you would need balancing valves to force the water from that first unit down into the fifth one. The other type of piping distribution system is what is called as reversed return. What you can see is basically the supply piping is the same, but now we have changed the return piping. What ends up happening now is that the supply goes to the first unit, so it has a shorter supply, and then when it goes to the return, it has the longest return. What ends up happening with this system is that usually the reverse return, because you're adding more piping, has a higher first cost. Though because all the piping is technically close to being equal, it is easier from a water balancing standpoint to balance that. Let's look at the typical piping hookups for a four pipe system. This is an old detail from a previous vendor that I worked at. This just shows a typical supply and return hookup or branch piping, run out instead of like that to the coil. Just going through it quickly, you have shutoff valves for isolation. You have flange or a union at the coil if you have to remove it. There's Pete's plugs where you can hook up a thermometer or a pressure gauge, balancing valve for balancing the water flow. There's a drain valve for draining the system if it's isolated for replacement. And then there's also a control valve, as the name describes, the control valve is controlling the water flow, controlling the capacity, controlling the temperature of the coil. Just point out that maybe there should be a strainer on the inlet to the control valve here, and then also too maybe there probably should be an air vent also to expel some of the air that's in the system. So now going to a single pipe system, what you have is now just one main piping loop that travels around to each of the terminal units. So this is technically the supply as well as the return piping. You would have it the same piping throughout. This is described in the ASHRAE handbook. Just laughing to myself, like what is actually a book anymore these days? And then also too, these books are updated every 4 years. So haven't seen the 2024 handbook for it, but this is a detail or information explained in the handbook. You have a different coil piping hookup from before. So with the single pipe system, here's a detail showing of the piping detail at the coil or your terminal unit. What you've done is you've added a small circulating pump, and you've removed the control valve as well as the balancing valve. You can see the primary circuit, and then there's your branch piping where that's located. What is the same as before is your shutoff valve. If you have should have a union for isolation, a drain, air vent, etc., like that. And then what will happen is with the single pipe hydronic systems, the main benefit of this type of system is that because you have less piping mains, you'll save a lot on your lower first cost. You'll end up with the same heating or cooling performance as a two-pipe system, so you don't have to worry about comfort, etc., like that. These are self-balancing, and then with the, I'll show you in a couple slides, but you're able to downsize your main circulating pump, and that will result in energy savings. These single pipe hydronic systems can be used for, primarily used for what I'll call them terminal units. A couple systems or just equipment just depicted here. You've got water source heat pumps, chill beams, as well as fan coil units. So what happens with the fluid temperatures on a single pipe system? So here is a schematic just showing 4 small terminal units. Let's just call them fan coils. It's a cooling system. You have a circulating pump. You have a chiller provided cooling for it. So your chiller is producing 42-degree water. In the left, that 42-degree water enters the first unit. It then comes out at 50 degrees. That 50 degrees then mixes with the 42-degree water, and the water temperature rises a little bit. As you can see in this example here, went from 42 to 44. So now the second fan coil receives 44.4 degree water entering it, comes out a little bit warmer, warms it up, etc. like that. And then finally, at the end of the loop, depending on how many units are operating at that time, what's the capacity of them also too, you have your delta T or your return temperature to your chiller. This is for a chill water system. Your hot water and condenser water systems are similar. And that, there's the just showing the last temperatures on the loop there. Now, in terms of pumping responsibilities, you have 2 pumps. You have a main circulating pump and then that little small circulator on the branch piping. So your main pump is doing the main piping system only. It's not going to the terminal units. And then just because you have a lower water pressure drop, you end up with a smaller horsepower, hence why you should save energy. There's just depicting the, where the main pump is circulating the water through. And then secondly, at the terminal units, you have a circulating pump. These are typically very, very small. They have a long service life, and this pump only runs when the terminal unit is on. All right, so once again, doing a similar VFD system on your main pumping system as your zones and units come on and off. With water source heat pumps, you have a coaxial heat exchanger, could also be a plate and frame heat exchanger. This is obviously shown used in cooling mode as well as heating mode. With the water source heat pump, here's a typical arrangement. You have multiple types of water source heat pumps. Picture up on the right just gives a plethora of different units there. You end up with a piping system feeding those water source heat pumps. And then similar to a chiller boiler system, you have a utilities or devices that are providing heating as well as heat rejection, etc. like that. So on a 2-pipe system, you have supply and return with just a single water source heat pump system. As expected, you have a single main that goes around, serves as your supply and return. You can see once again, why these are attractive, as you're eliminating a whole nother piping main. Could have, for renovations with core drilling, etc. like that, it might make it much easier to implement for a renovation project versus a 2-pipe system. And then once again, just to point out that on a 2-pipe system, you have control valves at each of the water source heat pumps as they turn on and turn off. And then a similar situation, but instead of a control valve, you have a small circulating pump that will turn on or turn off based on if your unit is in heating or cooling mode. All right, so let's talk a little bit more about design considerations with single pipe systems. I'll go over just the differences of how to work the mains and branches and runouts. I'll show a couple examples of the routing. And then just with chill water systems, want to just highlight that you still have to be careful with dehumidification control. And then I'll go over just quickly what the implementation is or things to watch out for with your hot water and water source heat pump systems. So first, let's talk about the pipe sizes. Pipe sizes have to do with velocity versus water pressure drop, also the delta T. Want to point out once again that piping main will remain the same size throughout. because we don't have any flow reduction. And then once again, just from, ASHRAE or old, rules of thumb, et cetera, like that. So your water velocities or your pipe sizes are still following the old traditional rules for your runouts and pipes and mains. All right. And then once again, I mentioned before, but your main circulating pump still has a VFD. Typically what is done, similar to before, is that the pipe size is sized for the full flow, but traditionally, depending on your system and diversification, et cetera, like that, your flow will run at 50 to 75% of the full capacity for 75 to 95% of the time, et cetera, like that. Here's just old-fashioned chart showing acceptable pipe sizes based on the friction loss and face velocity, et cetera, like that. Obviously this is always different for open or closed systems, whether you have copper steel pipe or steel pipe, whether your steel pipe is schedule 20, 40, 80, et cetera, like that. And then just, laughing to myself once again that this is probably all like computer based now or AI. And, I do have my little system sizer that you would, as you went through and size pipes and wrote it down and this and that, that's what you would, the little wheel that you would use to size your pipes. Anyway, so with pipe size and with sizing piping, you're doing a balancing act with velocity versus first cost. You're trying to find a happy balance. You don't want your piping to be too big on the left there because your velocity is probably lower than it should be, but you're adding additional first cost. But then you don't want to go, the other route where you're going very far to the left on this graph here, where you're really restricting or putting in much smaller pipes than you should have. What will happen is that will create a greater velocity, as shown in the yellow there, and then just higher pressure drop turns into higher operating cost, causes noisier systems, and then also creates more erosion inside of your piping systems, et cetera, like that. Next couple slides are just showing a couple routing examples of single pipe systems. This one here, you have parallel loops. You have your supply coming out in the center, and then loop 1 going up to the top, loop 2 going to the bottom. This is an example of a Love's truck stop, or I should say travel stop, that has a water source heat pump system. On the right is a mechanical room, and then they have a piping main with a loop that sort of runs in the center of the building. And then those red sort of rectangles are water source heat pumps. Each of those water source heat pumps would have a small branch pipe from that piping main in the center of the building. Just remember to include your expansion loops, et cetera, like that. You still have to put those in, whether it's a single, 2 or 4 pipe system. And then here's just a detail of the piping in the mechanical room. Very nice and clean, mechanic room. You can tell it's brand new. There isn't, hundreds of boxes in front of everything here, et cetera, like that. But anyway, this just shows your air removal system. Apologize, my color blindness or just terrible description of colors, but sitting on the ground on the lower right, like an orange or reddish brown thing, is an expansion tank. In the center there is a air separator. You can't see it, but there's 2 circulating pumps, and then the piping goes up to the building up in the upper left. And then this project here with the water source heat pumps was using a well field, and there's all that at the bottom going through the floor, all the individual branch piping that goes out to the well field. So there's a supply and return, et cetera, like that. Here's some other routing examples, just showing if you have a high rise with multiple floors, you would have multiple pipe mains going up to each of the floors. Here's, this is an example of a college down in North Carolina, a residential hall, It was a renovation going from one pipe to two pipes. It was fan coils. It was 9 stories tall. This was actually a case study where they looked at the reduction in piping to go from a two-pipe system to a one-pipe system. You can see it saved an enormous amount of piping of 5,000 feet, and then this turned into a savings of $350,000 on their first cost. Other examples are, alternate multiple floor loops. Here's a multi-campus one where you have a central plant, you have a main, and then each of the buildings has their own loop. And then from the loop, there's even more loops, et cetera, like that. Gets kind of loopy. And anyway, so next, let's talk about the equipment sizing. For the most critical one to look at is chilled water versus hot water and condenser water. All right, so we're back to our same schematic before, where we're showing our piping mains. We have a chiller. We have 3 fan coils on and 1 fan coil off. The intermediate piping, leaves a chiller at 42 degrees, and there's intermediate piping temperatures as the warmer return water, a little bit of return water mixes with the larger amount of supply water from the chiller. So with your mains, you want to account for diversity on the loop. So you can downsize that, but you want to make sure that each of the fan coils are sized for the appropriate cooling or heating load that you have for the space. What will happen is as the units travel, as the water gets warmer and travels down towards the right side of the fan coils here, your water temperature will warm up as explained. And you can combat that by just simply changing on some of the units a chill water coil to go from 3 rows to 4 rows, or to increase from, let's say, a size 2 to a 3. A lot of those changes there are just really incremental. As an example, a size 2 fan coil is probably the same size as a number 3. So while the cabinet, the fan, et cetera, like that, they just put a couple extra fins or a little bit, larger face area on the coil. So usually it's a very small add to increase your capacity of your chilled water coils. Typical chilled water coils, I'll say, is 10 degrees. I know that has risen in the last couple of years to 12 and 14, et cetera, like that. But for a single pipe system, you want to have it around 8 degrees. What you're looking at now is for your runout piping. This is the length going to the fan coil. You want to have a maximum about 15 feet away, 30 feet in total. And then a typical pipe size is 3/4 of an inch. Half inch might seem, either half inch or 3/4 inch. And then a rule of thumb with the number of fan coils on each of the loops, you want to have about 8 or 12. Once again, you're concerned about the last fan coil and the return water temperature. In this unit shown here, it's at 48.6, but we'll talk about the end of the water being experienced by the last fan coil in the loop. So for that last fan coil, you want to basically have a maximum entering water temperature of about 50 or 51 degrees. All right. And then at the end of the entire loop, you want to have a max of, say, 52 degrees. Now, why is this? Well, let's look at the water temperatures and then compare it to a site chart. So you want to keep your entering water temperature at, say, 50 or 51 degrees because you still want to maintain dehumidification control of your fan coil or your chilled water system. Just look at, a typical space is at 75 degrees and 50% relative humidity. So that 50%, that turns into a dew point temperature of 55. So basically you're looking at the difference, the delta T, between that water temperature 50 and 51, 52, et cetera, with a dew point temperature of 55. What will happen is if that water is too warm, you can't get enough cooling capacity out of your fan coil from that. So what are some ways to play with the water temperatures, et cetera, like that? You can, one thing to think about is you can reduce your entering water temp. So in this case here, to go from 44, say, down to 40. Just realize once you do that, then you're increasing the work that your chiller has to do. Can you do it with the same size chiller, or do you have to go up a size? And then the other option you can think about is, reducing the number of fan coils on each of the loops. And once you do that, you'd be increasing your first cost just because you're adding more piping mains, et cetera, like that. Excuse me for a second. All right. And then the other thing to consider, or maybe as a little trick to help out with your dehumidification control, is these terminal units traditionally don't have outside air into them, and you could have, or what's commonly done is to add a dedicated outside air system. And there is a way that you can use a thing called latent space load offset, where you can reduce your leaving air temperature to help with your cooling load, latent cooling in the space. All right. So just a quickly sidebar. Here's a quick slide just showing a dedicated outside air unit on the roof. Your zone cooling load is traditionally made up of two major components. Your outside air is typically handled by the DOAS unit in this case. The outside air has the majority of your latent moisture as well as sensible. And then your space cooling load that's often due to lights and solar, et cetera, like that, is mostly sensible with just a little bit of latent cooling in that. So dedicated outside air systems, the benefit of that is that you can decouple your outside air and your latent space requirements versus what's in your space. You can easily satisfy the IAQ codes, gives you a little bit of flexibility, more flexibility with the type of DOAS equipment as well as your fan coils. Easy to implement energy recovery. Hot gas reheat is easy to add inside of a unit, and then inside of your DOAS unit. And then the other thing to think about is traditionally these fan coil units, water source heat pumps and stuff like that. Traditionally, they were 1-inch filters. That is changing to 2-inch. That is changing from MERV 8 to MERV 13. But traditionally, those fan coils or terminal units don't have much fan oomph, I'll say, to overcome a higher indoor air, higher filtration, rating on filters, et cetera, like that, where you can easily accomplish that with a dedicated outside air system. Now let's talk about space latent load offset to help with the dehumidification in your zones. So a DOAS unit in this case is traditionally providing neutral air to the space where your dew point temperature is about the same as the leaving air temperature of the unit from a dew point perspective is about the same as your space. So what space latent load offset it is that we would then reduce the leaving air temperature from your DOAS unit to have a leaving air temperature less than your 55-degree dew point in the space. And then what will happen is that drier leaving air temperature is going to help with the latent cooling in the space. And therefore, since we're helping the space, the terminal unit, you'll require less cooling from the fan coil. So a smaller unit, less rows, warmer chill water temperatures are some of the possible benefits of implementing a space latent load offset with your DOAS equipment. Lastly, just let's talk about single pipe systems for hot water. Just because your hot water typically has a higher delta T of 20 degrees. I've seen them up in 30 and 40 degrees. Just because you don't have any dehumidification requirements, as well as, my experience has been that, don't get calls for lack of heating problem just because of you're designing for 0 degrees out, here in Philly, which, occurs every 3 years. And then also too, there's a lot of internal loads with people in light and sets like that. And traditionally, if you look at fan coils, typically the heating load is easily satisfied with a 1-row coil. And then just to point out once again that the routing of the hot water pipe follows the chilled water piping. And then just as a sidebar to help design professionals with assistance on single pipe systems, International Fan Coil has a selection software where you can implement your loops again like that. They have free design assistance, and there's also a 94-page technical guide that is available to go over all the ins and outs, much more detail and in depth than I'm trying to cover here in an hour today. Condenser water loops, once again, they're pretty flexible. Typical condenser water loop that I've seen has a delta T of 10 degrees, cooling as well as heating. And then once again, because of the water source heat pumps, their performance is not really affected that much by different temperatures. So say in this example here, just to exaggerate, the unit that is on the far left would receive 85-degree water. It'd be able to produce 24 MBH, or approximately 2 tons. And then if worst case, the unit that was all the way on the right had an entering temperature of 95 degrees. You think that's a big deal because it's 10 degrees. But really, because the water source heat pump essentially has a coaxial coil, it has very good heat transfer characteristics of this and that. So there really is not any performance degradation or reduction with the warmer entering condenser water temperatures on a water source heat pump system. And then once again, try to follow the max, how many units are on a loop, et cetera, like that. Okay, the last couple slides are just some generic design considerations. As I explained, over the years, didn't want to go through all the details, et cetera, like that, but just wanted to highlight a couple of things that, I wouldn't say I continually see, but these are the most often the problems are not done correctly with hydronic systems. So first, you have to be careful about air elimination. So your hydronic system is usually operating at higher pressure, but there are parts of it that could be operating at a lower pressure. So air and other gases that will get into the system, I put if, or you should say when they get in there. What will happen is that that air and gas is basically not water. So because it's not water, it's not transferring energy from the chiller to your fan coil to your system. So with the addition of air and other gases in your system, you'll end up wasting energy due to improper heat transfer. And then once again, from a pumping standpoint, from a pumping capacity, you have air mixed in with your water. You're reducing, obviously it makes sense that you're reducing your pump capacity. Other things that will happen, what to me is the most indicative item to show that you do have a problem with air and other gases in your system is that you'll hear excessive noise throughout your piping system. You'll hear it at your pumps. You'll hear sounds like marbles are traveling through your piping, et cetera, like that. So it will cause excessive noise. It could cause or could damage your pump impellers, which are sort of pain in the butt to replace, et cetera, like that. And then another thing too is air and gas in the system do have a corrosive, or just they are rough wherever they do accelerate the corrosion that is on the interiors of your pipes. So how can you get rid of air in your system? How to eliminate it? What is often done, or I'll say what I don't think is done enough, is to have small, manual or automatic air vents periodically through your system. This is just a typical detail here, just showing your piping coming from a terminal coil. You want to put a little T, a little pipe diameter, little straight pipe. What will happen is as the air travels from the coil and travels through your system here, the air will come to that T and the air will rise. Eventually, that air vent has the ability to remove the air from your system. You want to locate these on risers, basically any high point here. You want to locate them on, especially on piping mains. I see them not installed probably as much as they should, mostly on coils and terminal units. I would say I'd recommend to put them on a coil just because usually they have larger pipe sizes, they have a larger volume of water. Terminal units, do understand or do appreciate that this could get expensive at each of them, but maybe you would put one on, strategic ones, et cetera, like that, et cetera. So, and then just want to point out that you should put a little service valve. These are usually a little, I couldn't find a picture of it, but a little petcock. What will happen is that on the automatic air vent, it works just with a, I don't know, clapper, or not that type of clapper. Right, what will happen is, they periodically have to be cleaned out. And so the service valve obviously does its service by, shutting off the water, sealing your water system, and then you can unscrew the little air vent that's shown, here on this drawing. This drawing makes it look like it's like enormously big, but it's I don't know, maybe it's 3 or 4 inches tall, et cetera, like that. All right. Okay. Other thing that's important with air elimination is to install a expansion tank and a air separator. Just as once again, this is a typical detail from seeing that over the years, et cetera, like that. I'm not going to go into the function of each of, what the air separator does, expansion tank, make up water, et cetera, like that. And then I just have to laugh or chuckle to myself that, the term that I have here in italics or whatever is pump away from the expansion tank and the air separator. I had this so back in the sorry, sidebar, personal. I'm doing my Irish and I'm talking about something personal. But back in the 80s, I worked in New York City at a small mechanical contractor. And so we were doing work at CVS, like the television place CVS, and they were changing their steam heating in their offices to hot water. So us as a contractor, we got a job as a design build contractor to put in a small steam to hot water heat exchanger. And then we put in the hot water distribution piping for a couple floors and then fin tube and, baseboard or whatever. And so my boss tasked me with designing the piping, hydronic piping system. And okay, people, this was 1988, so there's no internet. And what books do we have in the office? I don't have anything from college or whatever. So I totally struggled, to do this and where to put stuff. So I asked this older project manager in the office, and I showed him my detail, and it was all wrong. And he basically like screamed at me, you pump away from the expansion tank and the air separator. And hence here it is on this piping schematic that I took a long reason to explain. But anyway, the reason you want to have these two devices in this location is that you want to create a differential pressure that's produced by the pump, and then also too, it's probably more important, is that the air removal or non-condensable removal is best happens, or you get the best effect at the lowest system pressure. And so your lowest system pressure is on the suction side of your distribution pump here. All right. So next thing, number 2 out of 3, that found out over the years is for chilled water systems, you always have to consider the amount of fluid that's in your system. What will happen is that if you don't have enough fluid volume in your system, your chiller will basically end up cooling the chilled water too quickly before it can get to your load, and then your chiller will end up short cycling. So this is a chart from years and years ago that I recently looked up again, and it's still pretty relevant. What they recommend is you add a volume tank or maybe oversight some piping to add volume. to your chiller. Just want to point out that for your volume tank, you want to add baffles inside them so that the water actually does mix and it doesn't travel from the inlet to the outlet. And then once again, rules of thumb is that if your chiller or your cooling system is for, what I'll call normal, HVAC or air conditioning duty, you want to have about 3 gallons per ton. But then if you're using that, if you have a chill water system that you're using for process or for low ambient, you want to increase that to 6 to 10 tons. One thing with process, HVAC, your cooling load like a day like this is pretty steady. Whereas on a process, we're kind of expecting it to be very intermittent. So it's like the unit is off, and then you have a request, the manufacturer has a request to turn on their manufacturing equipment, and boom, the chiller's got to come up and running. And then, side note, just check with manufacturers on their recommendations. And then also to always, for any type of equipment, add as much modulating control, to it, scroll compressors, VFD compressors, et cetera, like that. They seem to be kind of the norm once again today, whereas, dating myself, that was not the case years and years ago. You would add like inefficient hot gas bypass. So this is just a schematic just showing of a problem that I end up witnessing on a job that I sold, that we ended up with problem with short cycling. So I don't remember the exact tonnages, but basically we were working at a museum and they're replacing their chill water systems. We put an approximate 100-ton air-cooled chiller out, on a roof. We had a very large air handling unit that was serving multiple galleries that was right next to it. And then far away, we had, maybe 50 or, probably more than that, 100, 150 feet. We had these small, like I can remember 5 or 10 or 20-ton rooftop indoor air handling units. So if you took the calculation, okay, my chiller of 100 tons, and then include all the piping to those faraway units, I met my requirement of 3 gallons per ton. But in actuality, what ended up happening is that those other smaller units were offices and they were intermittent. And what ended up happening is basically the large air handler that was right next to the chiller ended up being a hog and using all the chilled water that was in the chiller. So we ended up with a problem of short cycling the chiller. So we ended up having to add a volume storage tank on the chiller there. All right. Other thing, just with fluid volume, is that the chiller has a minimum requirement for flow. So what you want to do is add a bypass or a 3-way valve. You don't want to put that in the mechanical room because once again you'll short cycle the water flow. You want to try to put it far away with a bypass, or it's easy enough to put in a 3-way valve for that. And then the last thing, not really I can't say a pet peeve, but the other thing that often comes up, we're in Philly here. It does get cold in the winter, not really as bad as it used to be, unofficial, global warming, sidebar, blah, blah, blah. But anyway, everybody knows water freezes at 32 degrees. If your ambient temperature gets below 32 degrees, you should add some type of freeze protection, or one of the options you can do is add freeze protection to your chill water system. Could be even hot water, et cetera, like that. So equipment that requires freeze protection could be air-cooled chillers, make-up air units, DOAS units. Also consider piping if it's passing through any unheated spaces. And also too, just remember that your chilled water system, if it's not drained down, if you have chilled water that's in an air handler, or especially a unit vent or a fan coil, if they have outside air, you have to be careful, or just remember that you have to do some type of freeze protection. Hey, maybe you're draining your entire chilled water system in the wintertime, or wintertime, that's a lot of work to do, or maybe you're doing it individually at each of the units, et cetera, like that. Another option is to add, antifreeze solution. just what is turned into the last couple of years is essentially just the use of propylene glycol. You don't want to use antifreeze that you can purchase like for your RV or for your cars, but nobody works on cars anymore. Just ethylene glycol, my understanding has gotten by the wayside just because if there's a leak, it does have some toxic or not good properties, et cetera, like that. So essentially for antifreeze solution, just for years and years, I've just seen the use of propylene glycol. So there's different manufacturers that produce propylene or glycol. Each of the manufacturers has a chart that that's shown here, unfortunately, in an ugly purple and grayish or whatever color that I'm terrible once again describing. But essentially what you have is the ambient temperature, and then you have two percent volumes, or you have volume percentages for freeze protection versus burst protection. So just want to go through the difference between freeze and burst protection. Freeze protection is a higher ambient temperature. This is the temperature where that ice, that glycol mixture, it is mixed with water, will start to turn to ice and slush. At this time, it still can be pumped, but eventually what happens is as the ambient temperature drops further, you'll hit what is called a burst protection. So this is at the lower ambient temperatures. This is in actuality when the solution does freeze and expands, and as the name implies, it will burst. So what is a correct percentage of propylene glycol? I've seen, when I worked in Buffalo, Buffalo was automatically 30 degrees propylene glycol, tried and true for years, et cetera, like that. Years ago, or just as I've moved, worked in Philly, I've seen different variations from 10 to 30%. But just to explain, show the difference. So if you have a 30% mixture of propylene glycol, your freeze protection is down to 10 degrees. Your burst protection is down to -20. So just, I'm in Philadelphia. So here is from ASHRAE, your annual heating design dry bulb temperature. So this is just showing that for 35 hours per year, the temperature, could get to 11 degrees. Once again, my experience, or just feels like, about every 3 years or so, we'll get a cold snap where it gets down to 11 or 0 degrees for a couple days, et cetera, like that. So just realize that when you are adding glycol versus your fresh water, the glycol has a lower specific heat versus water. So therefore you have poorer heat transfer. And then in addition, the glycol is more syrupy, so it has a higher density and viscosity. What ends up happening is you end up with losses of, additional losses through your pump, and then you have increased piping, friction losses through your piping and coils, et cetera, like that. So what is the correct percentage? Once again, I sort of bring this up. So sometimes I feel that the, engineers that I work with, I want to say they're wrong, but sometimes I feel they are conservative, but maybe they do put a little bit too much glycol in than what they probably could get away with. So just one thing is, once again, make sure there's different glycol manufacturers, but then also too, equipment manufacturers have different glycol D-rate ratings. Want to just point out that once you add glycol to a system, your ARHI certification goes out the window or by the wayside. Don't understand why this is done or why this hasn't been corrected over the years. But if you have a coil with fresh water, you can get an AHRI certified performance. But then once you add a glycol to it, you then get a statement that it says it's rated in accordance with AHRI, so it's not actually, third-party certified. Just want to point out that the percentage, it does greatly depend on the type of what I'll call heat exchanger that you're using. So what I found is that for coils, chillers often have shell and tube heat exchangers. There's usually a pretty significant D rate. But when you have a water source heat pump that has a coaxial coil, or plate and frame heat exchanger, there's not really too bad of a D rate. And then once again, just a kind of a personal preference or just a personal observation, selecting equipment over the years and years, et cetera, like that, that if you can keep your glycol percentage between 0 and 25, you're really not tapping into too bad of a D rate. It just seems that once you get to 30% or higher, the performance really takes a big hit, and often makes it difficult to achieve capacities and leaving air temperatures once again. So anyway, just an opinion or a tidbit of my experience, that if somehow people could live with 25% versus 30%, makes the performance of your system seem to me would operate a lot better, et cetera, like that. All right. So anyway, so coming to the end, we're at 12:53, a little bit too long with the story. Sorry about that. So anyway, just went over single pipe hydronic systems. Want to explain how we're can be used on the different distribution systems. It has lower first costs because you're essentially not running that second main, but you still can provide the same occupancy comfort. Just with design considerations, the main thing is to worry about or just realize that you have to account for the mixing of the water temperatures as you travel down the terminal units, et cetera, like that. And if chilled water, be careful of dehumidification concerns. This is probably any times with cooling or chilled water, whether it's DX or cooling, whether it's chilled water or DX, it's definitely consideration. And then just last pet peeve, not even a pet peeve, just what I've seen as a problem over the years is problems with air elimination, and then just sort of feel that the overemphasis on higher propylene glycol solutions for freeze protection. All right, so here let's start opening up for questions. Once again, to remind everybody that this presentation has been pre-approved for 1.0 professional development hours. So you can send, as David said, send myself or him an email. We can get to the appropriate certificate. And then just with Ambient Academy, upcoming webinars that we have on our schedule are for Tuesday, July 16th. This is on indoor air quality monitoring. And then after that is Tuesday, August 13th. This is a air handler presentation by an engineer at a custom air handling factory. And let me get out of this and try to. Alrighty. Okay, if you have any questions, feel free to type them here, or you can unmute yourself. Hopefully. David? Yes, the question is, will the PowerPoint be accessible? What we can provide is a copy of the slide deck, in PDF or Adobe Acrobat format. Don't be shy. Come and ask some questions. Okay, the question is, what was the international fan coil reference that you talked about? Let me just bear with me a second, Ryan. Let me just get back to that slide. So international fan coil is a fan coil manufactured located out in Oklahoma. They have what is called a SureFlow design, where I sort of, if I can just switch slides here. So they have an option, here it is. They have an option over here on the right. I'll expand. They have an option for a factory installed single pipe system that has a circulating pump on it and an isolation valve. So back to so IEC has that available as a factory installed option. And so they have available as a resource. There's a 94-page technical guide that's available online. If you want to send me an email, I can forward you the link for that. And then in addition, they also have computer software. This is a screenshot here that I'll try to expand once again. But basically with that software, they don't make it available to customers. They would like for the customer to work with the local sales force. But essentially what you can do is add up, you can basically make your loop systems where you put in your, how many fan coils you want, your fluid temperatures, and then your performance for each of the fan coils. And then this program will calculate the sizing of each of the fan coils, the capacity, and then in addition, it will also size like it will simulate the water temperatures as they travel around your loop. That's one of the difficult things is if I can just, it's poorly shown here, but just it's, to calculate, it would take a lot of time to calculate all these intermediate mixing temperatures by hand as you do it and such like that. So this computer program makes that much easier. Okay. Okay, Keith Davis, how do you determine the heat gain by unit for chilled water so that the end unit still get the correct temp for cooling and dehumidification? Okay, that was just explained here, Keith, is that this, you either do the calculations by hand or this computer software has the ability from IEC, IEC has the ability to perform that for you. Okay, the next question is the max unit per loop for 10 to 15 units, does that apply to chill water and condenser water? This was for condenser water, because you have a little bit more flexibility with the water temperatures, they recommend between 10 and 15. With the fan coil units, they recommend about a little bit less than that, between 8 and 12. And then there was a second part of that question. I wouldn't say there's a max tonnage per loop. It's more so, it depends on the size of, once again, it's more so based on, you could have a 10 1-ton fan coils, or you could have 10 3-ton fan coils. It kind of depends on the load, not on each of the loads, but basically just, how many of those 10 units will be on, what's the temperatures, et cetera, like that. The next question is no. So the question is the terminal unit pump variable speed? It's not. That unit, the main pump is variable speed. The terminal unit, the zone pump to each of the fan coils is constant speed. and then that is just on off. So there's a call for cooling, the unit turns on, the temperature is satisfied, the pump turns off. Okay. You're welcome, and great, I answered it. Thank you for letting me know. Always is a wonder. Okay, the next question is, can you please explain again why we need bypass for the chiller? Okay, I will apologize that this is a very poor diagram to explain that. All right. So with your chillers, you have a heat exchanger in them. So you'll size your chiller, say for 100 tons. A normal GPM is 2.4 GPM per ton. So at full velocity or full capacity, you have 240 GPM going to that chiller. That turns into a velocity of 10, just pick a number, 10 feet per minute through the chiller. With a variable pumping system, as your load reduces, what they'll do is they'll reduce the water flow, and they'll try to keep the same delta T across the chiller. But what will happen is through your chiller, through your bundles, through your heat exchanger, as your water temperature reduces, your velocity reduces. And then what will eventually happen is as the velocity will get too low, and it will kind of create laminar flow at the heat exchanger, and then you'll end up getting improper heat transfer. So each of the chiller manufacturers have a maximum GPM, which you never ever get to, but then they also have a minimum flow. So what could happen is, say that minimum chiller flow is at 50%, or, so what could happen is that, out in your system, your load can, you have two-way valves, so your load is reducing. What could happen is that the water flow through your system is less than what's on the bypass of the minimum of the chiller. So what they recommend to do, you have to keep the water above that minimum through the chiller. So what they recommend to do is to add, some type of bypass so that 50 GPM of water can flow out through their chiller, and then just use numbers. 40 GPM can flow through your coils, but then you'll have 10 GPM bypassing and then coming back to chiller. So I just want to point out is that for that bypass of that 10 GPM in my example, you don't want to have it in the mechanical room or close by the chiller, because you'll end up having recirculation, short cycling, et cetera, of the chiller. You want to send that slug or that mass of water out into your system, to a distance away. So you'll have you could have instead of a two-way valve, you have a small three-way valve. The other thing that I've seen is to have a two-way valve in the bypass. And once again, apologize that this is a poor diagram, that I have just really one piping shown with actually should be two. But the bypass is going from the supply to the return, and it's essentially needed at the chiller, and you're bypassing the water that goes out to your terminal